In this video, we will investigate the chemical shift of a signal in proton NMR. So chemical shift refers to the location of the signal on the NMR spectrum. And normally, the NMR spectrum ranges anywhere between 0 to 14 ppm. And the chemical shift of a signal in proton NMR is then set relative to a reference compound. And the reference compound is TMS. TMS stands for tetramethylsilane, and here is the chemical structure of TMS. So we see there are 4 methyl groups in here that is symmetrical. So the 4 signal from TMS would give us a signal, and we would then set that equal to 0 ppm. All other signals are then set relative to the signal from TMS. And we will find that all other protons would always be found on the left side of TMS signal or downfield from the TMS signal. To calculate the chemical shift of a particular proton in a molecule, it can be computed by measuring the distance downfield from a TMS signal, followed by dividing this by the operating frequency of the NMR machine. But the equation is something that we don't have to focus on. And below is an example of what an NMR spectrum can look like. So here is a signal from TMS. And again, the signal from TMS is set equal to 0 ppm, and everything else is to the left of it. And the highest chemical shift that we will find will then be 14 ppm for most of the proton signal. So proton signal would show up anywhere between 0 to 14 ppm. The closer the signal is to 14 ppm, we will then say that signal is de-shielded or downfield. Versus the closer the signal is to 0 ppm, we will then call this to be in the shielded region or in the upfield of the NMR spectrum. And there are 3 factors that can affect the chemical shift of a signal in proton NMR. So chemical shift is then listed here as sigma. That's the symbol of chemical shift. So the chemical shift overall of a signal is affected by 3 factors, and we call them as follows: sigma diamagnetic, sigma paramagnetic, and sigma nonlocal. Sigma nonlocal and sigma diamagnetic is seen to affect proton NMR, whereas sigma paramagnetic affects carbon NMR. Let's now investigate the first factor that can affect the chemical shift of signal in proton NMR, and this is the sigma diamagnetic effect. The sigma diamagnetic effect refers to the shielding or de-shielding effects that the proton can be due to the circulation of the 1s electron surrounding the hydrogen nuclei. So here is a hydrogen atom with a nucleus in the middle, and surrounding this nucleus is the electron cloud from the 1s orbital that the hydrogen has. And this electron cloud is basically protecting the nucleus from the radio frequency produced by the NMR machine. So again, the electron cloud is protecting or shielding the nuclei from the radio frequency produced by the NMR machine. Therefore, the more electron cloud that it is, then the more shielded the hydrogens would be. Versus if there is less electron in this electron cloud, then the more de-shielded this hydrogen nucleus would be. And we will then see that the electron density of surrounding the hydrogen nuclei is affected by the electronegativity of the nearby substituent. When this hydrogen is bonded to an electronegative atom, the more the electronegative atom that the hydrogen is next to, then the higher the chemical shift of that signal would be. So again, the 1s electron cloud is circulating the nucleus and shielding the nucleus from the external magnetic field, here in this case the radio frequency signal. So let's see what happens when the hydrogen is next to an electronegative substituent. When the hydrogens is next to or bonded to an electronegative substituent. The electronegative substituent is pulling, attract an electron from the 1s electron cloud away from the hydrogen nucleus, therefore making the hydrogen nuclei become more deshielded. And the more deshielded it is, the more to the left or the closer to 14 ppm that we will find the signal in. Versus if the hydrogen is to be next to an electron donating group. If the hydrogen is next to an electron donating group, the electron donating group would donate electron into this 1s orbital, therefore increasing the electron density in this electron cloud. And the more electron that it has in here, the more shielded it would be toward the external magnetic field. So therefore, the more shielded it is, the closer to zero that we will find this hydrogen signal would be in. And again, a substituent can donate or withdraw electron density from a hydrogen by either the inductive effect or the resonant effect. Let's now investigate some of this example. So first one, chemical shift as electronegativity increases. If we were to be comparing the chemical shift in here of this different hydrogen in here, then we will observe that when a hydrogen is not connected to any other electronegative atom, its chemical shift is 1 ppm. And if we were to have an iodine in here, again, this iodine would be taking an electron away from the carbon, and the carbon is then taking an electron away from this hydrogen, therefore making this hydrogen right here become more deshielded. So therefore, a chemical shift would now be higher, in this case 2.2 ppm. If we were to have a bromine rather than iodine, the chemical shift of this atom is now 2.7, and the reason is because bromine is more electronegative than the iodine. And next, the chlorine, 3.1 ppm, and lastly with the fluorine, 4.3 ppm. And the chemical shift is also increased as the number of substituents increase. So here in this case right here, if we were to have only one chlorine, it is 3.1 ppm. If the hydrogen were to be next to two chlorine, the two chlorine, both of them are pulling electron away from the carbon, and in turn this carbon would now be pulling electron away from the 1s orbital of this hydrogen, making this become much more deshielded. So therefore in this case it would be now 5.3 ppm. And if we were to have 3 chlorine, it would now be 7.3 ppm. So this is the sigma diamagnetic effect. It has to do with the amount of electron surrounding the hydrogen nuclei, dependent on what kind of group that the hydrogen is bonded to. It can either gain electron density from the group or lose an electron density to the group. If it were to lose electron to the substituent that it is bonded to, then this hydrogen right here will become more deshielded and show up to the left on the left side of the NMR spectrum. If it were to be bonded to an electron donating group, its electron density would become much thicker. Therefore, it can shield its nucleus better and therefore show up on the right side of the NMR spectrum. And now, let's investigate the sigma nonlocal effects. This effect right here is also called the anisotropic effects. And this is basically referred to the shielding and deshielding effect due to the electron circulation elsewhere in the molecule. So elsewhere in a molecule, there could be electron moving that would generate its own induced magnetic field. And the induced magnetic field can either align against or along with the direction of the external magnetic field. And in the case where the induced magnetic field align in the same direction as the external magnetic field, it will make the external magnetic field become stronger than applied and therefore make the proton field more deshielded. For an example, let's say here is the direction of the magnetic field, the external magnetic field, And here would then be the induced magnetic field generated by the electron circulation elsewhere in the molecule. If the induced magnetic field being generated elsewhere in the molecule align in the same direction as the direction of our magnetic field, then what will happen is that they would add together, and therefore they will combine together to produce a stronger magnetic field. And the proton would then be feeling a stronger magnetic field than what it would be, and therefore become more dishielded. However, if the induced magnetic field that is generated elsewhere in the molecule align in the opposite direction compared to the direction produced by the external magnetic field, they would cancel each other out. So therefore now a proton would then feel a weaker magnetic field, and therefore it will be more shielded. For an example, let's take an example of look at some of this example. First, for the aromatic ring. So here the benzene ring with the 6 pi electron in here. This 6 pi electron right here can be orbiting, circulating on top and on the bottom part of this ring. And this circulation of electron right here, again, anytime we have circulation of electron, it will produce its own induced magnetic field. And here in this case, the arrow in blue represents the direction of the induced magnetic field due to the circulation of electron in the benzene ring. And now, the hydrogen in the benzene ring are right here. And if we were to be looking at this, then we would then see that the hydrogen is actually pointing in the direction where it now is pointing up. So this part right here is pointing up. And the other part in here of the ring is then pointing down. So it consists of this part right here that is pointed up. And this part right here that is also pointed up as well. If the hydrogen were to locate in this region right here, it would be feeling the induced magnetic field in the direction that it pointed up. And this would then be in the same direction as the external magnetic field. Whereas if the hydrogen were to be found in this region, then this would then be opposite to the direction of the external magnetic field. And if the hydrogen were to be found in here, they would then say to be more shielded. But here in this case, because the hydrogen is found on this side in the case of the benzene ring, and this is the direction that is aligned with the direction of the external magnetic field, and because it is pointed up, so therefore the hydrogen will be feeling a stronger magnetic field compared to what being applied, and that's why it is more dishielded. So therefore we see signal for aromatic hydrogen show up anywhere between 6.5 to 9 ppm. And now let's take a look at an alkene for another example. In alkene, when we have a carbon-carbon double bond in here, then again there's actually electrons circulating in here. And due to the circulation of electron, the induced magnetic field would be as follows. So in this region in here, it is pointed up. And in the region in the middle, it is pointing down. If our hydrogen in the alkene come into the interact in the region in the middle, it would be shielded. But if it were to be found on the other side, it would be deshielded. So here in this case, this hydrogen right here show up in the deshielded region. And that's why its chemical shift is also higher as well. So here in this case, we see chemical shift for alkene hydrogen are anywhere between 4.5 to 6 ppm. And that is called the sigma non-local effects. And another example, the circulation of the sigma bonds electron can also generate a deshielding region as well. So again, in any carbon-carbon double bond, there's electron moving in there. And when this electron right here are circulating around in here, it would also produce its own induced magnetic field. And here in this case, these are the direction of the induced magnetic field. And technically speaking, it looked like something that we call the de-shielding cone. So any hydrogen that come interact in this cone right here, that would be the de-shielding region. So hydrogen that come close in this region would then say to be de-shielded because of this de-shielding cone, and therefore it will show up to the left side of the NMR spectrum. And if we were to be looking at this effect right here, by comparing the chemical shift of a tertiary, a secondary, and a primary CH. In this case right here, we see that the primary CH have the chemical shift of 0.9 ppm, whereas the secondary CH is now 1.2 ppm, and the tertiary CH is now 1.7 ppm. And the reason why is because when we have more of this carbon-carbon bond, there will be more of this de-shielding cone in here. And that can actually make this hydrogen right here become more de-shielded. And another example that is very obvious is in the ring. So in the cyclohexane, this hydrogen in the cyclohexane is actually more de-shielded compared to this hydrogen. And the reason why is as follows. Along this carbon-carbon double bond, there will be this de-shielding cone due to the circulation of the electron in this bond, and therefore producing this de-shielding cone right here. This hydrogen right here on the equatorial position align in the same direction as this cone, so therefore it actually more de-shielded compared to this hydrogen. And another example would be this molecule. So here in this case right here, between these two methyl group, this methyl group right here is more de-shielded than the other methyl group. And the explanation for this is as follows. There are pi electron movement in here. And at this pi electron movement in here, it may produce a shielding or de-shielding cone. And because this methyl group come close to it, it would become more de-shielded in this case. And finally, this perhaps is the most important table for us to focus on. All of the chemical shifts for all of the signal in proton NMR. So if we were to have a methyl CH, a chemical shift is 0.9, a secondary CH, then 1.2, a tertiary CH, then 1.7 ppm. And the allylic is anywhere between 1.6 to 2 ppm. The alkyne CH is now 1.7 to 3.1 ppm. Ketone is 2.1 to 2.6 ppm. So we can summarize the following. If it is bonding to a alkane, alkane would always be below 2 ppm. So from 1 to 2 ppm. The more substituted it is, the closer to ppm it would be. And if it's primary, it would be closer to 1 ppm. So that's how we can summarize that. Analytic, in this case, it simply would be closer to the 2 ppm range. And now ketone, this types of hydrogen right here next to a carbonyl. This is a very types of one types of signal that is very common that we would see in organic molecule. And the chemical shift would be 2.1 to 2.6 ppm. And benzylic is 2.2 to 2.5 ppm. So here in this case right here, and next alkyl halide, we would then see the chemical shift is anywhere between 2 to 4 ppm. The more electronegative atom the atom is, then the closer to 4 it would be. But it anywhere between 2 to 4 ppm. And when a signal is next to an oxygen, it would now be closer to 4 ppm. In the case of ester, they're now very close to 4 ppm. And if we were to have an alcohol, this hydrogen in here have chemical shift being anywhere between 0.5 to 5 ppm. And we will see that for alcohol, thiol, and amine. And alkene signal is anywhere between 4 to 6.5 ppm. and aromatic hydrogens are shown up anywhere between 6.5 to 9 ppm, and aldehyde about 9.5 to 10 ppm, and carboxylic acid 10 to 12 to 14 ppm. So these are the chemical signal of the different hydrogen that we will find on the spectrum. Let's now try a few examples to estimate the chemical shift of each of this signal and plot them on the NMR spectrum. So here in this case right here, let's do this. How many distinct signals would we expect to see for this molecule? First, this methyl group will give us one distinct signal. Let's call this signal A. And this CH2 in here will give us another distinct signal, and that will be signal B. And there's two C hydrogen in here, and that will give us the signal C. And this one right here will then be signal D, and this methyl group here is signal E. So overall, we will find 5 distinct signals for this molecule. Now, let's estimate the chemical shift of each of this signal. So here in this case, signal A, this is a primary CH. So therefore, we will expect to see this around 1 ppm. So it can be 0.9 to 1 ppm. And same thing for this one, 0.9 or maybe 1 ppm. They will be close together, but not exactly on top of each other. And now signal B, in this case right here, this is next to an oxygen, and this oxygen right here is an ester. So if we were to go back to our table over here, we would then find that that hydrogen right here will be closer to 4 ppm. So therefore, going back to this one will be around 4 ppm. And signal C, which is right next to a carbonyl, this is about 2.1 to 2.4 ppm. And the signal D, this is a second CH, so this is about 1.2 ppm. So those are the chemical shift of these 5 signals. So now let's draw its spectrum. So here is the NMR spectrum from 0 ppm to about 14 ppm. But here in this case, we don't need to plot this all the way up to 14 because the highest chemical shift we find in here is 4. So let's here make here 5 ppm. 1, 2, 3, 4 ppm. So we will first find this signal E around 1 ppm. So around 1 ppm, we will find a signal in here, and that will be the signal E. And about 2.1 ppm, we will find another signal in here, and this would then be signal D. Signal C would be about, so this one will be 1.2, somewhere in here. And that will be the signal D. And the signal C would be 2.1 ppm. So that would be signal C right there. And signal B is about 4 ppm. So up here about 4 ppm, we would see that signal B. And signal A would be about 0.9 ppm. So in this case, we will find another signal in here, and that would be the signal A. So that's how the NMR spectrums for this molecule would look like. Now please note that we have not described the shapes of this signal yet. We just plotted where the signal would be and their chemical shift. Let's now try another example. What kind of signal, what would be the NMR spectrum of this molecule would look like? So here in this case, how many distinct signals would we expect to see? So in this case, this CH2 will give us one distinct signal, and this one as well. So this one, let's call that signal A, and this is signal B. Now these two hydrogen in here are symmetrical, so therefore that will give us the signal C. And these two hydrogen in here are symmetrical as well, so that will give us the signal D. And this hydrogen right here will be different as well, and that is the signal E. So overall, there would be 5 signals that we will expect to see for this molecule. This signal C right here will be 2 times the intensity, and the signal B will be 2 times the intensity, and signal A will be 2 times the intensity. And the signal D would be 2 times the intensity as well, whereas signal E, it does only 1 times the intensity. So if we were to now sketch the NMR spectrum of this molecule, it will be as follows. So let's say here is 0 ppm, and now this one right here is 10 ppm, and now 5 ppm in the middle. So the signal A would be, let's now estimate the chemical shift for each of this signal. So for signal A, because this is next to a bromine, and we can see earlier on this table, when it's right next to a bromine, it is anywhere between a 3.4 to a 3.6 ppm. So going back to this one, about 3.4 ppm, we'll find the signal A. And now signal B is right next to a benzene ring, and we know right next to a benzene ring is about 2.5 ppm. So over here, 2.5 ppm, we will then see the signal B. And the signal A and signal B would be about the same height, since they have the same intensity. And now for the signal C is in the benzene ring, and that can show up anywhere between 6 to 9 ppm. So therefore we will see one signal from 6 to 9 ppm that correspond to the signal C. And signal D would also be the same thing, anywhere between 6 to 9 ppm. And then lastly the signal E, anywhere between 6 to 9 ppm. And now signal E would then be shorter compared to the other signal, because there's only one hydrogen that make up that signal. So that's what we would expect to see for this NMR spectrum.